The, the argument that we're going to make in the next few minutes, we have to go back to what is science and what distinguishes it from religion. Or I might call this episode of these little vignettes the "everyone knows is not a scientific argument" episode. Because everyone knows is not a scientific argument. A scientific argument is essentially saying, I have a theory. The theory predicts certain outcomes in the real universe. I run experiments, and the experiments give me outcomes consistent with the theory. Or alternatively, I run the appropriate experiments, I run them well, and I get outcomes inconsistent with the predictions of the theory. Then the theory is not a valid theory. So that's one of the criteria for a valid theory. So it's not based on who knows what or what expert said something was true or not. It's something we learned in high school. Science is based on hypotheses and testing of hypotheses and showing that the outcomes of these tests are in agreement with the hypotheses or not in agreement with hypothesis. That's all it is. Expert testimony doesn't really count here. Everybody knows doesn't count. Everybody used to know the earth was flat. Didn't make the earth flat. So in this particular case, we're actually suggesting that there's no data in support of the Pauli exclusion principle. And that's the overall basis. And that there's a better theory that actually predicts what we in fact observe. Well, one of my favorite philosophers of science is a fellow named Karl Popper. And I actually recommend, if you want to get back into the theory of science, that you read some of Karl Popper's discussions of this. Science is supposedly objective. We measure things over and over again, and then we say, all right, it's pretty certain that when we measure the ionization of helium, the first electron will require 24.6 electron volts. Many laboratories have done this. It's been repeated dozens, maybe hundreds of times. We see it in the solar spectrum. And we also know that when we ionize this beast and then we do a second ionization, we objectively see over and over again 54.4. Now, we don't prove those are the ionization energies according to Popper. We just show that this is the way the world appears to work. Proof, objectively, is not something you can do in science. You can disprove, but you can't prove. Anyway, you can get what we'll consider objective data. Because you can say, well, everyone who's sophisticated enough to run the instrumentation gets the same answer. This is a good number. We can believe it. So we know that helium, for example, has first and second ionization energies, which are very different. One's 24.6 and the next is 54.4. We're happy with this. So now the next step in the scientific process is to develop a hypothesis that explains or is consistent with these observations. If the hypothesis is not consistent with these observations, we better find a new theory. Because otherwise we're going to be making patchwork theories, sort of like what we learned in high school about how the Greek astronomers kept adding one more shell above the Earth to explain yet another planet. Oh, this planet's on this shell, and that planet's on that shell, and the moon is on another shell, and what we see in the sky are falling stars, those things with the tails behind them. They're not meteorites, as we now believe, etc., etc. So the theory got more and more cumbersome until it became obviously absurd, and it was, the best theory, of course, is the simplest theory. It was Occam's razor, saying simple is usually an indication of better and superior. And I think quantum mechanics, we're going to get to this point, has now reached the point of the shells, one shell after another, one failure after another, explained by an additional level of mathematical complexity. There's nothing brilliant about mathematical complexity. It actually just begins to hide the truth that there's a fundamental flaw at the very beginning of the process. And so that's what we're going to try to ask ourselves. Another plank that we have to look for, another hallmark of a good theory, is one that's consistent. So let's give an example apropos of what we're discussing today. Why is the Schrödinger model the standard model of the quantum theory? Well, it really relies on the fact that the Schrödinger model is an agreement with a certain set of data. That data belonging to the hydrogen atom. Schrödinger model predicts the correct excitation states, and it predicts the ionization energy. It says, oh, when you ionize hydrogen, it's going to take 13.6 electron volts of energy to remove the electron from hydrogen in the ground state, because the ground state energy level is 13.6. Now, consistency with that model would say, okay, then when we have a 2 electron atom, the ionization energy and the predicted energy level of the electron should be the same. So if we have a measured ionization energy of helium, which we do, of 24.6 electron volts, then the theory should say the electron sits at 24.6 electron volts. That would be consistency. So we're sort of stuck with that. Another plank that was added later to the entire edifice of standard quantum theory, we have to look for consistency here, is that both electrons are always at the same energy in the ground state of a 2-electron system. That's the so-called Pauli exclusion principle. So if one is at 24.6, the other one has to be at 24.6. And we've already, in the introduction, described how there appears to be an inconsistency between that requirement and energy conservation.